You know, we're practically swimming in data, right? It's everywhere. Information is just constantly coming at us from all directions. So the big question is, how do we turn all that noise into actual trustworthy answers? Well, that's exactly where statistics comes in.
All right, let's just jump right in with a classic head-scratcher. You see this all the time with national polls. It just feels wrong, doesn't it? How on earth can you know what hundreds of millions of people are thinking by only talking to 1,000 of them? It sounds like some kind of magic trick. But it's not magic, I promise you. It's statistics.
So what is statistics really? At its heart, it's a method. It's a structured way to ask a question, go out and get the evidence, figure out what that evidence is telling you, and then, finally, present a clear answer. It's the toolkit we use to find the signal inside all that noise.
Now, every time you start a statistical journey, you immediately come to this critical fork in the road. And this is probably the single most important distinction we're going to make today. Are you looking at absolutely everything or just a tiny piece of it?
So, down one path, you've got the population. This is the whole shebang. It's everyone you're interested in. If you want to know what all adults in the US think about something, your population is every single adult. That's the group you ultimately want to understand.
But let's be real. There's no way you can talk to every adult in an entire country. It's just impossible. So, we have to take that other path. We take a sample. We grab a smaller, manageable group that we can actually study. This little group is our snapshot, our piece of the puzzle that we hope represents the whole thing.
And that right there is the key difference. The population is the huge group we want to know about. The sample is the small group we can actually measure. The entire field of statistics is basically about building a really strong, reliable bridge between these two things.
Okay, so you've gone out, you've collected your sample data, now what? Well, the first and most direct thing you can do is just describe what's right there in front of you. No big guesses, no leaps of faith, just the facts about the data you have.
And this has a name, of course. It's called descriptive statistics. Its only job is to neatly summarize and organize the data you've gathered from your sample. Think of it like you're writing a short, clean biography of your dataset.
And it turns out, to write that biography, you really only need to answer two main questions. First, what does a typical value look like? We call this central tendency. And second, how spread out is all the data? We call that dispersion.
Central tendency is all about finding the center of gravity for your data. It's the value that everything else seems to kind of cluster around. And we've got tools like the mean and the median to help us find that sweet spot right in the middle.
Let me show you what I mean with a super simple example. Imagine this street with 5 houses. The mean, the average price, is $400,000. And the median, which is just the price of the house smack dab in the middle of the list, is also $400,000. So far, nice and tidy.
But, life is rarely that clean and simple, is it? So what happens when something weird gets thrown into the mix? Let's say a billionaire builds a giant $5 million mansion right at the end of the block. How does that mess with our story?
Whoa, okay, look at that. That one mansion completely blows up our average. The new mean house price is now $1.3 million. But look at the median. The middle house is still the middle house. Its price is $400,000. The median didn't even flinch.
And that's the big lesson here. The median is just tough. It's what we call robust against these extreme values, these outliers. So whenever your data is lopsided or skewed like this, the median often gives you a much more honest picture of what's typical.
Okay, so that covers the center. But what about that second question? How spread out is everything? I mean, think about it. You could have 2 cities with the exact same average annual temperature. But one has mild weather all year, and the other one has blazing hot summers and freezing cold winters. Same center, but 2 totally different stories, right? That spread is dispersion, and it's just as crucial to understand.
Okay, so describing our little sample is useful, for sure. But now we get to the really exciting part. This is where statistics gets its superpower. We're about to go beyond just describing what we have and start making educated guesses about the entire population. And this is what we call inferential statistics. We're using the evidence from our small sample to make an inference, a logical, educated guess about that huge population we actually care about. This right here is how those political polls actually work.
Now, you might be thinking, isn't that just guessing? And no, not at all. There's a really smart, careful logic that lets us make that leap from the sample to the population. It's a process called hypothesis testing.
Okay, so how does this logic work? Think of it like a four-step dance. First, you start off by being a total skeptic. You assume nothing interesting is happening in the big population. That's your null hypothesis. Step 2, you look at your own evidence. What did you find in your sample? Then comes the big one, step 3. You ask, if that skeptic is right, and there's really nothing going on, how likely was it that I'd see a result this strong just by pure random luck? And the answer to that question, that probability, is your verdict, the p-value.
So this p-value is key. If that number is super small, the usual cutoff is less than 5% or 0.05, it's like the universe telling you, wow, it would be a real fluke if this just happened by chance. At that point, you can reject that skeptic's view and say your result is statistically significant. It means something real is probably going on. So let's pull all this together. We've talked about two different paths, two sets of tools, but they're not separate, you know? They work together toward one single, really powerful goal: to turn raw, messy data into actual, usable knowledge.
And this table really lays it all out perfectly. Descriptive statistics is all about the what. It answers the question, what does my data actually look like? But inferential statistics, that's about the so what. It helps us answer the much bigger question, what does this little piece of data tell me about the entire world?
You know, there's this great quote from a statistician named Carl Pearson. He said, "Statistics is the grammar of science." And I love that. It's the underlying structure, the rules we use to build arguments and test our ideas about the world in a way that's clear and honest.
So now you've got the basics of this new language. You understand the grammar. The only question left is, what do you want to say with it? What important question about the world will you be the one to answer?